In 1650, an earthquake tore through the city of Cusco. Spanish colonial buildings, made with European techniques and mortar, cracked and crumbled within seconds. But less than 50 miles away, on a ridge 2,500 meters above sea level, something strange happened. A 500-year-old Inca citadel felt the same shaking, and it barely moved. That citadel is Machu Picchu. And by the end of this video, you'll understand exactly how a civilization with no iron tools, no wheels, and no written engineering theory built structures that have outlasted colonial architecture, modern buildings, and centuries of seismic violence in one of the most earthquake-prone regions on Earth. So where do we start? With a simple question: what makes a wall fall down in an earthquake? Most buildings fail because they're rigid. When the ground shakes, a solid fused structure has nowhere to release that energy, so it cracks. Concrete and mortar bind stones into one solid mass, which sounds strong until the ground moves, and that single mass has no flexibility left. It just breaks. The Inca builders at Machu Picchu did something almost the opposite. They used a technique called Ashlar Masonry, cutting massive stone blocks so precisely that they fit together without any mortar at all. Some of these joints are so tight that even today, you cannot slide a blade between two stones. And here's the part that seems counterintuitive. That lack of mortar isn't a weakness, it's the entire point. Without mortar binding them into a single rigid mass, the stones are free to move independently. Engineers who study the site describe what happens next as something like a dance. During a seismic event, the blocks shift, jostle, and resettle against each other, absorbing and redistributing the shock instead of fighting it. When the shaking stops, gravity and the precision of the original cut pull the stones back into their original position. The wall survives the earthquake by moving with it, not resisting it. But cutting stones this precisely, by hand without iron, raises another question. How did they even manage the shapes? Look closely at the walls of Machu Picchu, and you'll notice something odd. Many of the blocks aren't simple rectangles. They're irregular, polygonal, some with 10 or 12 angled sides, locking into their neighbors like pieces of a three-dimensional puzzle. One famous block, visible in the palace walls of nearby Cusco, has 12 distinct angles on a single face, and still fits its neighboring stones so precisely that no mortar was ever needed. This isn't decorative. Polygonal stones create far more contact surface between blocks than a simple grid of rectangles would. More contact points mean the load and the stress of an earthquake get distributed across a much wider network, rather than concentrating force on a handful of straight seams. It's the same principle behind modern shock-absorbing structural design. Discovered independently, roughly 500 years earlier, using stone and patience instead of steel and computer modeling. And that patience is worth sitting with for a moment. The Inca had no iron chisels, no pulleys, no wheeled carts. Getting a stone this precise meant grinding one block against another, by hand, for hours or days, using harder stones as abrasive tools, checking the fit and grinding again, until two faces of rock matched each other closely enough to hold a building together without a single drop of mortar. Every wall you see at Machu Picchu represents thousands of hours of that same repetitive, exacting labor. And the stonework is only part of the story, because the real secret to Machu Picchu's survival might not be visible at all. But before we get to what's buried underground, there's a smaller detail worth noticing first. Walk through the site and look at almost any doorway or window. Why aren't they simple rectangles? There's another detail hiding in plain sight in almost every doorway and window across the site. Instead of standing straight up and down, they're built as trapezoids, narrower at the top than at the base. That shape isn't a stylistic choice. A rectangular opening cut into a stone wall creates sharp 90-degree corners. And sharp corners are exactly where structural stress concentrates and cracks begin to form during an earthquake. A trapezoidal opening spreads that same stress across angled edges instead of a single sharp corner, letting the surrounding stone absorb the shock rather than fracture at a weak point. The walls themselves lean into this same logic. Many of them are built with a slight inward tilt, sometimes just a few degrees, angling toward the center of the structure rather than rising perfectly vertical. That small tilt lowers the building's center of gravity and works against the very forces that cause tall, straight walls to topple during violent shaking. It's a detail so subtle that most visitors walk past it without noticing, and yet it may be one of the reasons entire structures at Machu Picchu are still standing after 5 centuries of seismic activity. Machu Picchu isn't the only place these techniques show up either. At Sacsayhuaman, a fortress complex above the city of Cusco, Inca builders used the same mortar-free, interlocking stonework on an even larger scale, some individual blocks weighing over 100 tons. That site has survived the same earthquakes that leveled Spanish colonial buildings, constructed centuries later. Using techniques imported from Europe, the consistency is what stands out. This wasn't a technique invented once and left to chance at a single site. It appears again and again across Inca architecture, in different regions, at different scales, suggesting a building philosophy that was deliberately refined and repeated, not a one-time accident. Some engineers who have studied the site estimate that more than half of the total construction effort at Machu Picchu went into work you'd never see standing on the surface. Foundations, retaining structures, and an extensive drainage system carved beneath the terraces and buildings. That's a staggering allocation of labor for something invisible. Why would a civilization pour the majority of its effort into what's buried underground? Because water is one of the fastest ways a mountainside city destroys itself. Rain saturates soil, soil shifts, foundations sink unevenly, and unevenly settled foundations are exactly what turns an earthquake from survivable into catastrophic. The Inca built stone channels and drainage systems that still function after 5 centuries, pulling water away from structures before it can weaken the ground beneath them. Some sections of this drainage network run directly beneath the terraces themselves, layered with gravel and crushed rock in a sequence that modern engineers would recognize as a filtration system, letting water pass through and drain downhill instead of pooling and softening the earth above the buildings. Combine dry, stable foundations with a masonry system built to flex, and you have a building that isn't just earthquake resistant. It's earthquake resistant because the ground underneath it was engineered just as carefully as the walls on top of it. But what if the flexible walls and the hidden drainage still aren't the whole picture? Then there are the terraces. At first glance, the famous step terraces cutting across the mountainside look purely agricultural. And in part, they were. But they served at least one more function. Terraces break up a steep slope into smaller, stabilized sections, each with its own retaining wall and drainage layer beneath the soil. That structure helps prevent landslides during heavy rain, and some researchers argue it also helps absorb and dissipate seismic energy before it ever reaches the buildings above. Whether that was a deliberate seismic strategy or a byproduct of good agricultural engineering is something scholars still debate. But the effect is the same either way. The mountain itself became part of the defense system. Here's where things get genuinely strange, though. Some archaeological research points to a major earthquake, estimated above magnitude 6.5, striking the region sometime around 1450, while Machu Picchu was still under construction. Damage from that event may have reached ceremonial structures like the Temple of the Sun. If that timeline holds, it means the builders of Machu Picchu weren't just designing for a hypothetical future earthquake. They may have watched their own current techniques fail in real time and adjusted, mid-construction, toward the flexible, mortar-free style we still see standing today. It's a compelling theory, also one that mainstream archaeology continues to investigate rather than confirm outright. Which brings us to the question nobody has fully answered. Trapezoidal doorways, inward-leaning walls, polygonal interlocking stones, terraced slopes, hidden drainage networks. Was all of this the result of a coordinated, intentional seismic engineering philosophy? Or did the Inca simply build with the best techniques available to them for reasons of stability, aesthetics, and durability, and get remarkably lucky that those choices also happened to resist earthquakes? Historians studying the site are honestly split. Some see too many independent seismic-resistant features working in concert to be accidental. Others point out that many of these techniques, like Ashlar masonry, were used throughout the Inca Empire, in regions and buildings that had nothing to do with earthquake preparation, suggesting the resistance might be a side effect of a broader cultural building standard not a targeted defense system. What we do know is the result. Structures built 5 centuries ago using bronze tools, wooden livers, and no written blueprints have survived earthquakes that leveled colonial buildings built with what was at the time considered superior European technology. Modern structural engineers have taken notice. Some seismic engineering teams studying earthquake-resistant design have specifically referenced Inca joint patterns when researching flexible foundation systems for buildings in high-risk zones, particularly in regions of Peru and Japan where large earthquakes remain a constant threat. The core idea, allowing a structure to absorb and redistribute energy rather than rigidly resist it, is now a recognized principle in modern seismic design, sometimes called base isolation. The fact that a 500-year-old civilization arrived at a working version of that same principle using nothing but stone, geometry, and centuries of trial and error is part of why this site continues to draw structural engineers alongside historians and tourists. So the mountain keeps its secret, genius or accident, intention or fortunate coincidence. And if a civilization without iron or the wheel could build something this resilient into solid stone, it raises an uncomfortable question about the next site on our list. Because if Machu Picchu's survival came down to precision stonework, what happens when the material itself is the mystery? What if the secret isn't in how the stones were shaped, but in what they were made of? That's a very different kind of ancient technology, and it's still, in some ways, better than anything we can replicate today.